All right, next up we have Nuzhdin from ASML, who's going to tell us about Julia in C world, fast, safe, and seamless. So Yuri, please take it away.
Yes, thank you. Indeed, we in ASML, we're really looking how to integrate Julia on our machines. We actually have a much deeper talk about all this tomorrow at main stage at 11. But in this part, I will just focus on one particular aspect of this big trouble, is how to actually coexist with the existing algorithms. ASML produces a very complex machine. We have a lot of interfaces. We have a lot of interfaces. They are made with C, C++, Python, not with Julia. And now we start introducing the Julia, and it's just a few. But we cannot just make it as a model that exists in its own space. It actually needs to communicate to the machine back and forth. Hence, we need to call it. We need to call C, and we need to be called from C. Of course, this is not the first time we tackle with this problem. Other people had this kind of challenge. But in ASML, we also have an additional challenge that we use internally, our internal DSL to describe those interfaces. And it's not really like C++ oriented, so CHYGGX wrap was not really a feasible option. It's more like C-based, and I will explain you what it is a little bit later. But first, what is actually available? So assuming that we need to talk to C, what's available? Well, great documentation from the Julia. It really tells you how to integrate it, but it's intended for the C developers. It's the same problems every time, right? If you want to know how to manage memory manually, if you want to know what is the pointer and how the segfault looks, that's your choice. We said that, okay, this is very nice. This gives you reasonable performance. This gives you actually quite good performance. But if we want to make it available not only for our C engineers, but also for our engineers who just work with the models, they don't need to learn all this complex stuff, which is kind of available as well, but it have a significant performance cost. So everything in this documentation is very unsafe. But if you just can afford to copy all the data inside of Julia, then it's not a problem. In our case, it is a problem because we process a lot of data and it would be really slow. So what do we actually... Okay. Something went wrong. Is it? Anyway, we want to make our engineers able to write regular Julia code. Some example you can see on the left. It almost seems familiar, right? There is one special macro. This is about our internal DSL description, but everything else looks like a code that you can write. But it actually works with the interfaces and the structure definitions from this internal DSL, but it does it in very transparent way. Why? Internally, we pass the pointer here. This is what happens under the curtain. So people who just work with the models or with the algorithms, they don't see it. But internally, it's past the pointer. It's wrapped in one wrapper. It's wrapped in a memory safety wrapper. And it's also probably went through the interface adapter. And you don't see it. You just interact with it. And in this talk, I will just talk you through how we're making those wrappers. So if you want to have something similar in your use case, you can kind of use it as a reference how it can be done. So let's start about our internal DSL. It's very simple. It was invented somewhere in the 90s. So it's really C-oriented. It supports structs. It supports vectors as a dynamic entity. It supports arrays as a static entity. It supports strings. It supports primitive values. And it actually can allow you to define interfaces and call them back and forth, right? So you can implement your own interface and you can be called. It have a bindings to C, C++, Python, and that's what we introduced, Julia. And it also hides a lot of, it's a kind of great tool for us because it hides the remote connections, it hides IPC. It's very nice. And we have to use it. So what does it really offers us? Okay, first thing first, of course, primitive types. In Julia, it's very easy because primitive types are also first-class citizens for Julia. Julia really understands them. There is one specific case of enum, which is in binary is indeed represented as integer, but in Julia it has a special meaning. That's the only thing you need to care of. And one nice convenience for us is that all primitive types that we use are inherited from the number. So part of the code can be really simplified by not mentioning all of them together. Vectors. Well, vector is a simple thing. In our case, it just contains the pointer to the, this is what I wanted to like represent. It contains the size and the pointer to the data. And in our case, well, this is how it works. If we want to work with them, we have to define certain methods, and we use the methods that Julia defines for the abstract arrays to work with the abstract arrays. So we overload them. So if you start using the vectors directly, you don't see that it's wrapped in something, right? Which allows you to say, okay, if this code can work with something that looks like a vector, it keeps working with something that looks like a vector. I highlighted here propagating bounds. You will see it many times on the slides. And it's a very nice mechanism which allows you to play with the safety checks, right? Because in principle, working with pointers is unsafe. The pointers can change, the pointers can get out of scope and all this kind of stuff. So there is a lot of mechanism built in for pointer safety. But internally, when you already know that the pointer is safe, you can actually opt out. And Julia, with this propagating bounds, really gives you a very nice tool to semantically correct, to do this opt-out thing. I know it's fine. It's guaranteed. It's risky when you, as a user, claim this because maybe you checked it wrong. But as a library internals, it's really useful to switch it off at a certain moment. Structures is, in principle, same idea. We have a pointer. Well, we know how the pointer is structurized. It has fields, etc. You need to take care of memory alignment. And we have internally, we have a kind of big problem with that. We have several memory alignment schematics for some reason. So, but in general, if you're a C developer, you're familiar with memory alignment and how this done. You just work with the pointers, and the nice abstraction that we found is that our structures, they don't return back. For example, here we have a get property, right? So get property is what is called when you say a dot something. Okay, in this case, you can actually generate this kind of code. This is generated by the macro. And you can see that it just returns a pointer value. This is the nice way how we found how we can actually express back to the system that's the value. You need to take care of it. And because we do it in such a way, and it's also inline, it's static call graph compatible. So we as soon as we introduced inlines here, it became static call graph compatible. It's very nice for us because we use this feature. This is how we deal with the structure. So this is first layer. Pointers have the data access wrappers. Data access wrappers just explains to the language what we can do with this, right? Because structures have fields, vectors have elements, primitives doesn't have anything. They would be just the pointers. Next layer. Next layer is memory safety. As I said, this is returning still pointer. It's still raw pointer. Nobody guarantees that it's a valid pointer. You can think about all kinds of use cases. For example, you passed the value inside of the function, but developer decided to put this value in a global. Well, you don't know at which moment this pointer becomes invalid. So we need some invalidation mechanism. And we need a safety around it. The schema that we found to deal with it rotates around one interesting concept where we create this just a Boolean, but we purposely make it mutable, which means it always sits on a heap. And then we have this owned mutable wrapper, which takes care not only about releasing the pointer, if it can be released, but it also always carries this safety flag. And the idea is that as soon as safety flag is raised, it's safe. If it's lowered, it's unsafe, and you need to go through the acquisition procedure, right? Of course, for the root object, the one which was given to you directly, you can kind of know it's the pointer that I get when the function was called. It's still valid while I'm in this function. But for the sub-elements, it's not guaranteed, because you need to think about use cases like array got resized, vector got resized, and it was reallocated somewhere else. In this case, we track these sub-elements with index mutable wrapper and field mutable wrapper, and you can see that like field mutable wrapper is x dot something, and this is your field, and x square bracket something is your index. So we actually know. Yes?
So is this like implementing a shared pointer or something like this?
It's not really a shared pointer. It's just tracking the pointers and where they originated from. And I will explain how it works right now. So this is how it works. Let's say we get a structure which have a vector, which have some sub-elements, whatever. So far, it is great. It's fine. But somebody decided that this vector should be resized. So we created a new element in the memory. We don't know, actually. We don't make an assumption that it is safe. We just mark, OK, it's unsafe now. All of these wrappers, which points to the particular elements in this tree, now pointing to the safety, which is lowered. And by the way, you cannot raise the safety. It's just like restricted. We overload the function. So what do we do now? When we access to the certain field, the field says, OK, I'm pointing to the lowered safety. I need to restore it back. And then it goes through the parents, right? Because all of them have parents. Eventually, it goes to something which says, oh, I own the pointer. I know it's safe. In this case, it goes directly to onMutable. It says, OK, I'm safe. Here's your new safety element. I will attach it to myself. And you can attach it to yourself as well, right? So now in a heap, we have safety which says, I'm unsafe, and the safety which says, well, now I am safe. But only this element is pointing to it, right? What if we access this element? Well, say, I realize that you don't see the mouse pointer. I'm sorry for that. Can you see it now? OK. Something went wrong. Can you see it now? Yes. Sorry for that. I was showing everything on my screen. That's not good. Right, so that was the element that we reacquired, right? Those are not reacquired yet. Let's say we access here. Well, this one is saying, OK, I need to reacquire. I'll go to the previous one. Oh, this was also unsafe. It doesn't know if it's the same pointer or not. It will reacquire itself, and it will go to onMutable. And it will find, and onMutable at this moment will tell, that's my root pointer, maybe it's a new one. And you know that this is certain offset, right? It's indexed mutable. It keeps inside, I'm element number 2, so it can just recompute what's the new position in memory. And at this moment, it says, OK, I'm reacquired. I will point to this new safety. And the same here, if it's a field, it says, OK, I'm field X, and I'm required as well. So all of them are pointing to the safety. They are happy to report back that you can use us. This one is just left for GC, right? If they will fail reacquire, then you will have a runtime exception. And that's how you know, OK, maybe this element was removed from vector completely. Right? This is the safety mechanism that we have. Let's go further. Further is interface wrappers. Why? Because we want to have higher level, high order function structures, right? We do a lot of math in essence, and as I said, the type system of our DSL is very limiting, so we build something on top of it, right? And the matrix, in essence, is just like a size of the matrix plus data, which is represented in a vector format. And we support, like, at this moment, we just focus on like matrices, tensors, and sparse matrices, which is very nice. The downside of this approach, as I said, we overloaded a lot of base functions to make and feel those memory safety pointers behave like vectors and behave like structures, which actually solves the problem of writing the code, which works with it. It doesn't solve the problem of type system. I think it's my mistake that I did it in such a way that you can work with them as vectors, which sounds like why? It's actually convenient. Would be much more convenient if they would be inherited from abstract array, for example, for the vector. I was really lost in a type system then. I will redo this. I will not advise you to do this. Just make interface wrappers for everything. It doesn't really cost that much. I remeasured it. Julia really able to optimize all this out. It like really removes all these 3 layers of abstraction. It just says, okay, this is how we work with the pointers. That's it. But it saves a lot of hassle with interaction with the code, because now your code can be more strictly typed. You can say, well, this works with abstract array. You don't need to make a wrapper around it. But I didn't do it. And then I had to make a wrapper around it. So now developers are forced, if they throw it in their code, they can just say, okay, this is any, and Julia will figure it out. But if they send it to some predefined function, they wrap it in a DD array view, which hides internally array, and it has the safety mechanism, and internally just knows where it's acquired. Nice. For me, it was at this moment very convenient to say, well, the matrices cannot be resized. This is fine. This really simplifies both wrapper and life of developers, I believe, as well. Same here for sparse matrix, and if you can see here for a DD array, unfortunately you have to define a lot of, it's a trivial code everywhere. I didn't print it because it's obviously how to measure length of this structure, but you have to define all of them. You can read documentation to find which interfaces to define, or you can just take a screenshot. For sparse matrix, I'm happily surprised how less you need to define. You just do this and it works. The only trick was insert bank. You can look inside sparse arrays to see why. So you can omit it, but then the performance will not be that great and it will not be static compilable. Yeah, and in general, this is my mistake. This is like how I did like resize. Well, resize is not existing in Julia, but all of these things, I made it so you can transparently work with it, and it will pretend that it's a structure, or it will pretend that it's an array, which is nice, but again, I don't advise you to do it like that. Just make wrappers around everything. What's about performance? Because in the end, this was done for 2 purposes. One, writing the Julia code. As I showed you on the first slide, it looks exactly like a Julia code, so no problem with that. But what's about performance? Does it really solve it? I took one, I simplified one of the examples. Of course, we do the modeling, but in essence, this model was really like, we sent something which looks like a gigabyte of data inside of the model, we update it a bit, and then we take it back, and then back and forth. Back and forth was the biggest problem, because you not only copy it inside of Julia memory, you also copied it out. That was a requirement of the system, but yeah, if we can save half a second, we could, but we could not. So here you can see just back and forth, very safe, very easy, 1 second, run in 1 second. Ideal way is, well, you don't do this. You just have Julia code for the whole system, very nice, super happy. This is the measurement, this is like 10 microseconds, very nice. And you can see that overhead exists, like the third one is pointer-based access. So it actually ensures the safety all the time. It makes sure that it's fine, but actually the overhead is not that high. And if you say, this is just for subarray of size of 100, which is actually not usually the case. It's usually around 1,000, and then it's, of course, then it's kind of on par. You don't see big delays because of that, which actually allows us to work with the data which is located somewhere in our system, and back and forth. And I'm not showing on this presentation, but it's not only that we implement a model which is called by the system, but this model actually calls the system as well. And because it's a symmetric interface, then this data goes back and forth seamlessly, and the performance impact is really, really low, and Julia gives you all abilities to do that. So that's the memory safety mechanism. I saw that I will spend much more time on explaining this. I didn't went to like function pointers, etc., but they are really, really specific for how it's internally organized on us. And I would admit, I would like to make this open source, but for obvious reasons, like it's an internal DSL language, I cannot really make it completely open source. And I struggle to find what's actually useful. I think like safety mechanism probably useful, maybe structs are useful, how we deal with our internal definition of vectors, probably not useful at all. So if you are sitting and thinking like, okay, they actually did it really nice and it seems to be working and we may need to have similar approach, just reach me out and we will find out what we can share, what we cannot share, and how can we help each other. Because I think in the end, it would be nice to publish part of it, but that's my small request to you. If you see a value from it, just let us know, and we'll figure out something. And I invite you to our talk tomorrow, where we will talk about JuliaC being used to actually compile all this code plus the models and deploy it on a machine, and how we struggle with it and how it was a success for us. And if you're interested, also talk to us more about our use case of deploying Julia algorithms on a machine in a close to like stiff real-time environment. We have a lunch at 12 tomorrow in one of the rooms, so please join as well. We would like to hear your stories. We also would like to hear how you tackle the same problems. We're really curious to know what's going on in the industry in the same way. And yeah, that's the end of my talk. I'm waiting for your questions.
One question, I guess, that came up to my mind in the safety mechanism, and the answer might just be, I don't care about that, is thread safety, right? So I know it's a difficult question. I mean, the answer might just be, yeah, we only have one thread running, so it doesn't matter. But like, is there a way you can do thread safety? You could say like, oh, all access have to be, like safety access have to be behind a lock or something like that.
We did not look into this because it's one of our limitations. This interface was really made, this DSL was really made before multi-threading became a thing. It just non-reentrant, so we don't have a use case for that. I think it's possible to make something thread safe there, but it's also like intended for JuliaC, which is at this moment is also like not really there to have multi-threaded environments.
Yeah, I imagine it was something like that, so thank you.
So yeah, the short answer is like, this is not thread safety. No, it's unsafe, no.
Yeah, thanks for the talk. So you talked a bunch about this kind of pointer safety mechanism. So and I think one of the issues, let's say, is that you're working with raw C pointers, which kind of allow anything. So let's say you work with something where actually on the C side you have much stronger guarantees. So actually, maybe you're in C++, and maybe you have already some shared pointer or some kind of more safe pointer. Do you think that if you get more guarantees from the C side of things, that kind of erases most of the issues that you have in the interface?
No, it's actually intended to catch. Yeah, you can start defending it from the C side, but you still have the Julia side where you actually make interface which doesn't reveal that you do this, which means that on a Julia side it can go completely wrong, right? And because it still works like iterators in essence, right? It have all these problems which Julia doesn't have by not having iterators. You can save iterator, it's a variable. You can put it in a global, and then half an hour later you can access it, and it would be pointing somewhere, unfortunately. And you need to catch this. So it's a really prevention mechanism that from Julia's side you cannot have seg faults.
And maybe some static analysis? Would that do you think that could resolve some of these issues, or would it be too challenging?
I think it's quite challenging indeed.
Thank you.
I'm kind of cheating because I know some of the things behind this. But I noticed that you don't talk about any of the words that we run into, any of the problems. Could you just quickly say where were the things where we got stuck, or actually you?
Well, I think I mentioned that the interface I'm not super happy with, but in essence, that's not that difficult. I mean, of course, you need to be really careful. Most of the problems I had was accidental seg faults because I did not really understood the ABI of our interfaces, which also appeared to be fluid, but like, let's not talk about this. As soon as you do something right here, and as soon as you can write a C code which should do these operations, you can easily write the equivalent Julia code which will do it exactly in the same way.
And with trim, with Julia C?
Trim, yes. Trim, we had some problems with that. This is why I highlighted inline. For example, inlining, because this builds very deep structure. By default, Julia thinks this is too deep to analyze. By marking everything inline, you actually solve it, because then Julia is forced to really analyze it. And in essence, this is streamable. This is type stable. Yeah, you just need to hint Julia what to do with that.
Great, thanks. Well, I remember that sometimes code was removed from these parts, but that was a different story.
Another round of applause for Yuri. Thank you very much.
Thank you.